Hi, and welcome to AI at ORU. We started this seminar series to raise awareness of different perspectives of AI founded here at Örebro University, and also to inspire new kinds of collaborations. Because we truly believe that AI and autonomous systems will help to solve some of our biggest societal challenges, as well as making life better for billions of people around the world. Today's theme is AI and the design of the built environment. And I have two guests here in the studio. Welcome. Merhaba, professor here at Örebro University, and Vasiliki Kunduli.
Hello.
And you are doctoral candidate in computer science as well as here. Yeah. It's going to be really interesting because I heard the definition of wayfinding, and the definition was the definition was when the building communicates with the building user. So we will get back to that. But before that, we will start a short video with Amy Lutfi, our Pro Vice Chancellor in Artificial Intelligence and Innovation. So let's find out how Örebro University works in the field when it comes to AI in terms of education, collaboration, and research, of course. Thank you.
Hi, everybody. My name is Amy Lutfi. I'm a professor in information technology, and I've been working in the field of AI and robotics now for the past 20 years. And I'd like to tell you a little bit about our journey of how we've been working with artificial intelligence. So at Örebro University, we've been driving research, education, and collaboration in AI for a number of years. Our research is placed at the Center for Applied Autonomous Sensor Systems, where we have today over 70 researchers who are looking at the fields of AI, and this includes methods within machine learning, but also other AI technologies, who look at robotics and autonomous systems, and in particular, who look at the integration of AI and robotics so that we can create the next generation of intelligent systems that can work with and for humans. When it comes to education, we've been trying in the past few years to integrate AI in a meaningful way in several different types of education programs. We have, for example, our engineering educations, but we also have been looking at other types of educations where we feel AI is an important aspect in the education. For example, we've just recently implemented a revision of our law program where now they have an opportunity to take part in the developments of both AI and digitalization. Collaboration is essential for us at the university. And one aspect in terms of education and collaboration has been running a number of competence development initiatives. We offer courses for free to the industry as we see that information about AI is so essential to come out to all different types of industries. And we now have a specialized program called Smarter, where industry partners can come to the university, can share their different AI challenges with us, and together we try and find new solutions to these problems, but also increase their level of awareness and competences about AI. We find that by working with industry in terms of education, we also lift new research problems that feed into the research environment. There are a lot of different aspects that need to be looked at when it comes to the implementation of AI. It's not just the technical ones, but also legal aspects and aspects about IT infrastructures that are important to see. Our aim and our vision is to create a sustainable ecosystem around AI. When I say sustainability, I mean that all the different pieces of the university need to feed into each other. We see that the research feeds into education, the education feeds out into industry and collaboration, and these awaken new research questions which feed back into the research environments here at the university. In this way, we hope that AI can be an instrumental tool in confronting some of the biggest challenges that we have before us. and that we can show how AI can really be used for the good and the betterment of society.
Oh. Okay. Welcome back to the studio. And remember, if you have questions, please put them in the Q&A and I will pick them up in the end of this session. So welcome again, Mehul and Vasiliki. It's so nice to have you here.
Pleasure.
Yeah. So I learned I have learned earlier, like if I look on a poster, I will look at it, I will read it like a Z. And I wonder if the same thing when you walk into a building or something like that. So it's going to be really interesting today to listen to your talk. And I know that you met each other in Germany, right? Yeah, and you're from India and you're from Greece. So how did you end up in Sweden?
I will start maybe. So, firstly, thank you very much, Susanna, for organizing this series. It's a pleasure to be able to connect to a wider audience in the university and outside. So very pleased to do this. Before coming to Sweden, I was working as a professor at the University of Bremen in Germany. At the interface of AI and cognitive science, particular focus on spatial cognition research. And prior to that, I have been doing my PhD in Melbourne, Australia, where I lived for several years before I moved to Germany. And originally I am from Mumbai in India, where I studied economics. So I had a major shift of disciplines at some stage and when I went to Australia. While I was in Germany, I of course came across this very interesting position that was open in Örebro. And I'd heard very good things about living and working in Sweden, and I gave it a shot, and then I'm here. That's the short version of a very long, convoluted story.
Happy to be here. Thank you for the invitation as well. I'm from Greece, and my background is in architecture. So when I finished my degree in architecture, I was interested to do a bit of research of how people navigate environments and how the tools we have as architects are helping in the process. So I started doing some research in the area of environmental psychology, and then I was interested to see how new tools, for example, in AI can be helpful in this process. So that's why I did the internship, and this is how I met Mehul in Germany. Then the next step was a very big initiative from the university here when they were interested in aging from different perspectives. So that's why I ended up here doing my PhD in a quite interdisciplinary environment. That was really important for me. Yeah.
Wow. And now you are actually working together. And so how did you decide to work together? How did you found this kind of and we're going to do this project together and so on?
Well, we were already having some collaborative history on related themes while we were in Germany. And when I came here to Sweden, at the same time, incidentally, there was the newbie program of the Örebro University that was starting, and Vasiliki found a scholarship to start her PhD at Örebro. And since we wanted to continue working together, we thought this was a nice set of circumstantial affordances that were available to us, and that's how we started working together again.
Yeah, well, that's great to hear. Yeah.
Excuse me.
Yeah, no worries. Sorry. No worries. So let's find out, let's listen more about your presentation. I would just let the word over to you, and you can start to present what you want to share with us.
All right, terrific. Great. So we're going to share this presentation. It's a joint narrative trying to show broadly two facets of our research. One is rooted in artificial intelligence, the other in cognitive science. But it is very closely intertwined with each other. People often talk about interdisciplinarity and the need to talk to other disciplines, but here we have a unique situation that Vasiliki was originally an architect and then came into cognitive science and now is pursuing a PhD in computer science. She's actually directly within our department and an environment. So this is interdisciplinary research at very close quarters. Going into the talk, we will talk more about this as the presentation progresses. I thought I'll start a little bit with a reference to the work of Rem Koolhaas, who is a Dutch architect. I really admire his work, his creativity. And the image that is on the screen right now is the Seattle Public Library. So at the end of this talk, if you don't remember anything, please do remember this one building and try to pay a visit to it if you are in Seattle. The reason I'm bringing this up is it's sort of one quotation that he's made in a slightly different context, but I'm going to use it for my purposes, is the following. A building has at least two lives, and the one that is imagined by its maker and the life that it lives afterward, and they are never the same. The gist of our research is to use AI methods or develop AI methods that can help architects and planners and designers to navigate the space of design possibilities that exist in the imagination of the creative person, and at the same time to also envision what may or may not go wrong once the building has been started to use by its potential occupants in its particular context and its particular function. And we want to bring in the behavioral aspect and the more computational or AI aspect towards addressing the exploration of this kind of design spaces. Coming to the title of the talk, AI and Design of the Built Environment, I am aware that we may have a very interdisciplinary audience here from different faculties, so we will try to not go very technical, but rather give mostly a summary of the motivations and the big questions that inspire us to pursue this line of work. But there will be some references along the way for those of you who might be interested to look at some technical details. So yeah, please look at the references if you want to look at those details. This is the vision statement, which I am directly quoting from a paper that we wrote back in 2016 or so. And we are pretty Catholic about pursuing this. I haven't changed the word since then. How can cognitive modalities constitute the foundational building blocks of design education, design discourse, design systems and technologies, and even the professional practice of spatial design for architecture? That's the essence of what we are doing here. And as I said before several times, you need perspectives from AI, spatial cognition, or more broadly cognitive science, and of course the theory and practice of architectural training and design creativity. All of these disciplines have to come together to address a vision of this scale and magnitude. I'll hope that some aspects of this vision and how we try to achieve it will be visible in the remaining part of the talk. What do I mean by people-centered design? Simply put, trying to anticipate all possible users that may be relevant in a given design context. How do you design for children? How do you design for emergency situations? What happens if a building was in fire? How would people behave if the building was in fire? How to take care of the diverse needs of people with different kinds of cognitive requirements. People may have visual impairments, people may have physical impairments. So how do you take into account all the different perspectives? How about aging, for instance, which is something that Vasiliki particularly focuses on as a part of her PhD. So this is generally the conceptual canvas of people-centered design. And when I talk about cognitive modalities, I'm talking about investigating the cognitive modalities of vision and locomotion and other aspects that people use in their everyday interaction and moving around in the world. Let's start with an example. There are many different paradigms of computing for design. So here's an example of one of them, which is called parametric design or parametric design computing. You see a chair, and there are some parameters that control the structure of the chair. So there's the angle of the seat, there's the front angle, there's the height parameter, and there's the weight parameter. And you could imagine that there's some sort of a computational system or an algorithm that can find different possible combinations of these parameters, and each one of them would then give you a final product that might be different, and it may perform in some ways and it may not perform in some ways. That is conceptually what parametric design is really about. Going beyond the chair, whenever you see these kind of curvilinear forms, you can be pretty sure that some kind of parametric design system or parametric approach is behind the design of environments such as the ones that you see on your screen right now. Here's one example from the London Aquatic Centre. which was opened as a part of the Olympics that was organized in the UK. And this was particularly in the news for a range of reasons. They encountered some trouble. So people who would sit on the upper parts of the aquatic center, they were not able to look at the swimming pool. So the question is, how can a problem like this creep into a design of this magnitude? It's a very simple example. This is it's not very complex to check for visibility constraints or visibility requirements in these situations. But nevertheless, as you can see, Zaha Hadid, a very, very influential architect, sadly passed away recently. Somehow unfairly, a lot of blame was put on her. But I think I could give another talk on the reasons behind this failure. It's what I would attribute to the last mile problem, if people are aware of that. But what I want to say is parametric systems, they are basically a computational tool, and they need to be guided in the right way, with the right motivations, with the right requirements. And the way they have been conceived and developed so far is not people-centered. It's not cognitively driven enough. To look at it once again, so here on the right, you see essentially, this is a metaphorical way of sort of communicating to you what is a parametric hammer. It is essentially giving you an ability to give a shape to the outer envelope of the environment. But this is not how you determine what is happening inside the individual lives of the people who are going to inhabit this building. That requires being able to anticipate the fine-grained behavioral aspects of how people are going to move around, what they are going to see when they move around, what kind of collaborations may happen because of this, how may you inhibit certain kinds of patterns, things like that. So we are talking more about cognitive design from the inside, whereas the more standard approach in these kind of systems is to look at design as a piece of art from a bird's eye view, without much regard to what is going to really happen at the micro scale in the everyday lives of the people who are going to inhabit those structures. Let's come back to AI. AI and design may look a little bit far apart, but they actually are not. People in AI would know who Herbert Simon is. For others, I'd like to repeat. He's one of the most influential figures in AI. He conceived of the field of AI back in the day. Originally, he was an economist, also behavioral psychologist, and also a recipient of the Nobel Prize in economics. And he wrote a book, I believe in the late 60s, I may be mistaken with the exact time, called The Sciences of the Artificial. And there's a chapter in it which is dedicated to the science of design. And he considers AI and design to be some sort of duals, two sides of the same coin. And this is not exactly a quotation, but my interpretation that design, according to him, is a decision-making process under the constraints of physics, logic, and cognition. And in the previous example that you saw from the London Aquatic Center, I believe that the physical constraints have been respected very well, but some of the more logical requirements and the cognitive outcomes related to the cognitive visual perception of the people have not been respected. And one question that one could ask is, well, how do you take such computational systems and bring in the physics, logic, and cognition as one part, in one holistic framework? And that has been one of the crucial mission of our research in this line of investigation. Let's look at one more example. Here's the front end of a very typical architecture design tool. This is from ArchiCAD, but you could pick any you like. They would pretty much look more or less the same, even if they are internally not the same. The typical abstractions that are accessible to a designer are pretty quantitatively driven here. So these tools force the designers to think in terms of points, line segments, polygons, very geometric and quantitative thinking. Whereas if you are a designer or a planner, you may have the best of your intentions to think of people-centered requirements. You may think of mobility and visibility, but the tool simply just handicaps you in not giving you a direct usability or accessibility of these kind of human-centered features in it. And in the end, the tool naturally just becomes, I think this is a nice comic I found. This is essentially what a computer-aided design tool ends up becoming. The designers are forced to do all the human-centered thinking essentially by their hand. So the technical challenge here is to build on top of these kind of systems from a practical point of view and bring in those cognitive human factors which are not supported by them as primitive foundational building blocks within these systems. The other big problem with these tools is they force the designer to think of a design as a frozen moment of perfection in time. And the design is anything but that. We all know the design comes to life. A building comes to life when you put people in it, when people interact and do things, when they move around. So in reality, things are very different. There's action and interaction and dynamics in the world that needs to be taken into account. So two things. One is the foundational building blocks need to be cognitive, and the other is the design tool must give a way to anticipate the multimodal interactions that are going to happen in the environment. Pretty critical requirements. So let's go back to the parametric system example. Here, what's happening is there are some conceptual blocks and the distances between them, the proximity between them is being optimized. By optimizing, I mean you may try to maximize it or minimize it or use some other threshold of interest. Now, I would regard this to be as a low-hanging fruit. I couldn't resist bringing in this image of apples from my backyard here in Örebro, which I love very much, the feature in Örebro here. But to make the point, it is a very simple problem. And the real challenge really is, in view of what I've told you before, is to anticipate all the actions and the interactions, what would happen to people who are moving around on a wheelchair, what kind of relationships would they form, what kind of mobility patterns would they inspire or hinder. You even see some things like how would sunlight influence the dynamics of the shadows in the world. So the range is pretty. This is not an exhaustive example. I've taken it from a movie because it serves my purposes of example. It's from the movie Dogville by Lars von Trier, but I hope conceptually it communicates what I'm trying to get at. This is not from a movie. This is an example of a prototypical system that has been in the making since several years. I would emphasize it's not a commercial product, but it's meant to be a demonstrator of different kinds of capabilities that I have been talking about. So here you see that an empty space is being structured, it's being carved out into different configurations, keeping in mind some human-centered requirements. It tries to identify how zones are connected. What you see here is two-dimensional, but please take my word for it for now that all this, of course, is in 3D. Human mobility and perception happens in 3D, so it would not make sense to do this only in 2 dimensions. I will maybe have I will not have time to go into all the details, but I want to give at least 1 or 2 examples of what is the underlying essence of how these computations actually happen within the AI system for design. Essentially what it does is it tries to look up the shape of the empty space. A lot of the geometric modeling and thinking in design happens by looking at the physical things in the world, whereas what we are saying is, no, it's not the physical things. The empty spaces that are resulting are more important. So if you have a room that you are designing for a new office space, for example, it will look like a very spacious room, but you start putting a table, you put several other objects, you are subtracting real space. And what is left is the empty space that is left is the real space where all the interactions will happen. So let me make one example of this. All right, no, before that, I want to make another point. In the previous demonstration where the system was carving up different shapes, what was going on is it was trying to anticipate how mobility patterns, as you can see, a person can go left or right from the main entrance. This, by the way, happens to be the Gulbenkian Museum in Portugal, in Lisbon, Portugal. The system tries to anticipate what are the salient objects that may or may not be visible, and so on and so forth. And based on some designer specified requirements, some of these configurations might be important and some of them may be considered not so optimal. And that's basically what's going on under the hood. And here you get a bit more of a 3D perspective than in the previous demonstration. The system is also able to basically narrate the experience of the user, as you'll hear right now.
Going through the room, the visitor can see some windows all around, some doorways all around, and some pieces of furniture all around. The visitor follows the room's linear flow. The room seems crowded and continuous.
Right. I could not hear the audio, but I guess others did, and it made the point. So what's going on is the system is basically computing all the possible experiences that people will encounter. It might be worth it to look at one thing. It can actually summarize the entire experience for you. It not only computes the geometries, but it also gives a summary in natural language for the designer to understand. It even considers counterfactuals or hypotheticals. So something like, if you remove wall Y in room X, the circular ring structure can be converted to a hierarchical structure with room Z serving as a central hub. These forms of computation are very powerful tool in the creative problem solving of the designer or the planner or the architect. I talked about the shape of the empty space. That will be my last example before I hand over to Vasiliki. So here you see the real geometry of some environment that is being designed. If I remember correctly, it's a university building somewhere in the US. And the green zones that you see this is the truly empty space that is there in the world. And all the blue regions and the pink regions, these are what we call spatial artifacts. So for example, if you put a camera in the building, the camera had some sort of a range space. So you may want to say that some things may be inside or outside the range of the camera. Now, the range space of the camera is not a physical entity. It is not a material object, but for all conceptual purposes, you can treat it as one because you need to account for that space and you can actually subtract that space. So the next demo will give you an example of what happens when you, instead of the geometries, you focus on the truly empty space. So now incrementally, we'll subtract all these functional spaces and other kinds of affordances that come from interactions. And what will be left in the end will be the truly empty space that can be used as a basis of further analysis. And you can see now, compared to the physical geometries, this looks so completely different. And yet most conventional, or I would say, I don't know of any computer-aided design tool that takes this kind of a mindset in trying to anticipate people behavior. Once you have this empty space, you can do a whole bunch of things with it. This is what was visible in the previous video where the system was computing different possibilities. So you can compute how, whether or not a wheelchair will be able to pass from a certain space. Will there be a path that is private? Can you avoid certain security cameras or certain kinds of sensors? What will a navigation pattern look like if there's an emergency? Again, these are some examples, but they're only limited by one's imaginations and the limitations of computational geometry, so to speak. Whatever you can implement, you can just extend this. We have some examples based on what we think are really useful in architectural planning. Now, all of this can be done before a building has been built. And inevitably, no amount of technological intervention is going to solve all problems, which means there will be problems afterwards. So the question is, how do we analyze these problems that happen afterwards using a systematic approach? And how do we use that knowledge to influence the conceptual design phase in the first place? And this is where I guess I would like to hand over to Vasiliki to give some examples of that side of the work.
Of course, yeah, sure. So as you can see in this diagram here, the second part of the focus is on post-structural or post-occupancy evaluation. So how we can use empirical studies to deep in to see the experience of the users as they navigate the space. And we have done numerous studies in real-world situations. You can see some examples here from 2 hospitals in Parkland Hospital in Dallas in Texas, but also some train stations in Germany and also a hospital in Santiago in Chile, while we have a number of people navigating a space, trying to find a destination, and we are using technologies, for example, eye tracking or GPS, other type of video to see how they are performing and also how their attention and their orientation is changing in the process. So a systematic way to approach that will be, first of all, let's say the eye tracker to see which are the points in space that they're focusing on. While we also trace their route, we see where they're going, how much time they spend in different locations. We can analyze decision points that are really important for navigation purposes. At the same time, analyze the morphology of the space to see where is the light, how this influences maybe the head turns of the people as they're moving around. In general, the visibility of the space we can all sum up the situation, this experience of people, for example, in virtual reality, when we can have the experience of 20 people as one, and this can give, for example, this possibility to an architect to step in the shoe of someone to experience from his side a building. This can also have different applications. It really depends on the domain of interest. For example, in situations we are talking about, for example, a shopping center or navigating in a really large-scale environment, we are interested about the path, the turning of people, but also how they interact with specific areas or objects. And so the idea is either to have an understanding of individual perspective, but also to be able to aggregate the experience for a specific group of people, for example, for older people or people with wheelchair specific groups. So we are interested in some questions that are mostly related to visual perception and spatial cognition. For example, why people get lost during this process. And to make it a bit more specific, we can say how the rotational morphology of the space or in the path is affecting this behavior, and which can be environmental characteristics that can help or not help this experience. For example, we are also interested to see which are the people who get mostly lost. Maybe there are people who have never been to this place before, so it has to do with familiarity, but it also may have to do with some other kind of cognitive related skills. And concerning the visual attention during the process. So we're interested to see, for example, how the visibility in a building in specific decision points is really important for the wayfinding performance. And while we collect all this information through behavioral studies, the next step will be to define these behavioral results in some precedents that we can use for design. And one way to do that will be to define them as parametric constraints that can be embedded to design systems. And then from this point, we can generate different morphologies that respect cognitive related aspects. This is an example from the Parkland Hospital again, when we had 25 people from different age groups from 20 to 85. In this case, we were trying to see how they will reach a specific point, the pharmacy, while they had to change many different locations, take turns, take the elevator. We are focusing on, for example, specific aspects of visual range in specific moments, also how they turn their head, if they're fixating outdoors, and how this is really reflected in their performance. We end up with a list of precedents. So you can see some examples here. We saw that visibility in relation to some manifest cues of the signs or the landmarks were really important, as well as geometrical characteristics, for example, how much they had to rotate during the path. We can see an example here. We saw that as the building make people, the morphology of the building make people rotate, they have a problem to reorient. And of course, this might be a bit easier when you have some reference point, but it's well known from spatial cognition literature as well that this is there's a problem in the process of rotating. This extensive rotation creates some problems in spatial updating. So we want to see how design can contribute on this. And for example, a precedent that came up from that, it's that we need to ensure that everyone has visual access to some landmarks or signage during key positions in a route. So for example, you can see an abstractive way to represent that when we have a route and we try to create visual connectivity lines that connect decision points with a landmark. And in order to do that through a constraint in a parametric design tool, you can see an example here how this can be implemented. In this tool, we design this precedent by saying that the designer can put an opening, like a window in this corridor, in a way that we can be sure that as the participant, as the person is moving on the corridor, he will have access to this landmark outside. And the way to do that is to restrict him to put the window outside of this circular range. Of course, there are many other precedents and examples that come up from these behavioral studies. We saw some example from the rotation metric. So how you can maybe change the turns and the angle that someone needs to rotate in a path. It can also be other aspects related to the size of the corridor, how spacious it is or how narrow it is. And this really affects the way people navigate the space. It can be also related to the symmetry. Symmetrical spaces are easier to configure and understand while walking. It might also be related to visual attention. For example, clutter affect how visual attention works during an active navigation process. Of course, bringing all these things, this aspect together in the design process, this doesn't really mean that we end up just simplify all the plans, but the idea is that to give to the designer the tools to decide and anticipate human behavior so he can make the right choices of which is the most important thing and which is the level of complexity, how to find the balance between the geometrical aspects and the behavioral aspects during navigation. And of course, this is a process that can develop and become better and better. We saw some examples of how we can move from behavioral studies to precedents and to implement them during in design through design constraints. So this is a circle of evidence-based design. And of course, by designing and refine an environment, we can also go back and do a post-occupancy study again and learn new things that we can embed in the systems. So this is it's a dynamic process of learning. And I think at this point, I will give it back to Mehul to summarize.
Okay. I will take a minute to just summarize. So broadly, today we focus more on AI for architecture design and the built environment. And that's one applied way of looking at the foundational research, which is driving this kind of work, which is namely the confluence of artificial and human intelligence. And by human intelligence, I should narrow it down maybe to spatial cognition and visual perception. And we are particularly interested in combining analytical and empirical methods in the service of this AI and human intelligence research agenda. There are four critical pillars that are of interest to us. They are about human visual attention, human interpretation of the world in embodied contexts, how do humans anticipate events, and the multimodal interactions that humans engage in their everyday activities in different situations. Not to imply that there aren't other interesting pillars, but time and resources are always limited. So these four things are central to our undertaking. And these things can be investigated from a great many perspectives. And I think primarily, we are in the computational, cognitive, and formal side, but of course, there are philosophical aspects and engineering aspects and semiotic aspects coming more from humanities and social sciences. They are also relevant, and especially in Örebro in the last couple of years, we have started to make links with other researchers working on multimodality from those perspectives. And you can expect us to maybe in the future come back with AI for some other context and to show those kind of interdisciplinary connections. And the applications that we have over the years, by we, I mean my previous colleagues and the collaborators that still work with us in Europe and internationally. We've been looking at several application domains, but right now, architecture and creative media design and autonomous driving somehow have taken the center stage. And of course, today we focused on architecture, but perhaps there will be an occasion to go into autonomous driving, which is the second part of Vasiliki's PhD research, and he will be defending soon in a few months, so you can hear more about the autonomous driving part then, or maybe in a future talk. So thank you very much for this opportunity, and that was all from us insofar as the talk is concerned.
Thank you. Very interesting to hear. So I'm looking forward to your future project as well. If I come back, if I walk into a new building, do you know where should I look? Like, where is the most, where's the most view my eyes will look at when I walk into a brand new building? Is it like the Z, or is it like up or down, or have you keep track on that?
I think it really depends on the structure of the place that you are entering, and also what's really happening there. Maybe there are some features that really work as landmarks. For example, if you enter a hospital, you will most probably see a desk, of information desk in front of you. So I don't think it really works from A to Z. There are pillars of most attractive things that you will focus first, most probably.
Yeah, and I could add to that no two buildings are the same. Even if you look at two hospitals, you cannot say that what will work in one hospital will work in the other case. So one message maybe which I should have alluded to before, and I'm glad you asked me this question, is that all of these technological interventions, they are not value judgments on how to do things, but rather they are like exploration devices that you give in the hands of the designer to find the optimal solution that they have in mind for a given problem context. So let's say you walk into a hospital. I'm sorry to use this case. I hope you don't have to walk into a hospital, and nobody has to. But let's say you do, and you are in the emergency wing of it. Now your constraints and your requirements in this situation are very different. So the Parkland Hospital study that Vasiliki mentioned, here this was the precise situation that we were working on. People would come to the emergency section, and typically they would have to go and find the pharmacy. And it turned out the pharmacy was an approximate 15 to 20-minute walk through a convoluted series of turns and twists and so on and so forth. This is pretty challenging if especially you have come to visit someone who is in an emergency, or if you yourself have some physical issue that you are dealing with. So in this context, the solutions that you will try to encounter by doing a study in the community, they'll be very different to what you would do, for example, in terms of what are you going to notice if you enter a museum. So it will be the specifics of the context of the situation that will come into the picture. There are some general pearls of wisdom that can be said about what attracts attention. So for example, motion is one of the most critical factors in directing somebody's attention. Luminance and changes of color come much after that. So if you look at human visual perception, the focus that we can really have is roughly 4 degrees in front of us. So that's the thickness of my arm at a distance of an arm's length, so to speak. That's as much as you can see in focus. Everything else is not in focus. And there are other features in the environment, like what is moving and what is blinking. These kind of things are already done at the level of the eye, even before the brain gets a chance to say something about what might be of interest. And most of vision actually happens in the brain, not in the eye, really. So I don't know if I'm still answering your question, but there is no universal solution about where somebody will look that is devoid of a context. You need the context, and what we care about is how can we have systematic techniques that will at least let you explore the space of possibilities and give you some ranking of what one should do and what should not do. But in the end, the decision really is in the hand of the architect or the planner.
Thank you. Let's see if there are any more questions in the Q&A. No, it's not yet. Please put them there if you wonder something while we have both of you here at the same time. Speaking about hospitals, like, can it be too many signs or instructions how to find your way?
You can go.
Too many. That was one of the questions we had from the designers when we did the study in the hospital, because their idea was that maybe if we add more and more, that will be helpful. And that's the line of work they did when they tried to to build the new one. What we saw in all the new cases, we saw that the most important thing was like where the signs were positioned, and what is also on top of the signs. If there are other landmarks or the way that people are do decisions in specific decision points that affect their navigation performance and experience in general. So it's not quantitative only the answer, it's really quantitative as well.
Yeah, and I would like to add that, yes, indeed, there's an expression I'd like to use, death by signage. Or this happens in many different situations, typically at airports and shopping malls. One thing we have seen in many of our behavioral research is that designers would spend a great deal of time or an investment on putting some signage at a place where they think they should put it. And when we do study after study, we see nobody was looking at it at that point. So there is this multi-objective optimization here of how many do you put, and at the same time, where do you put? And this is where this large-scale multimodal analysis that we do, where we get clusters of information about where do people typically get lost, that help us determining where to put the signage. So yes, you can go overboard with your signage, or maybe perhaps other kinds of devices also. And you can also do too few, and that's the challenge of it. Find the middle ground.
And I bet it's not only like science. It can be like,
absolutely.
Can it be like audio, like music or something like that, or like I don't know, colors, the design of the walls. I don't know.
Definitely.
Yeah, it can be like that as well.
Yeah, great point. I want to add, especially this connects to the rotation problem that Vasiliki introduced. So people familiar with train stations in Germany, for example, would notice that when you get off the train and you go down the stairs, there's a very symmetric structure to them. And it's often hard to determine, even if you belong to the city, whether to go left or go right. And this happens for a range of reasons, and the rotation problem that Vasiliki mentioned. But one trick would be to color them differently. That would be a very simple solution, because this will help you automatically form a memory of your directionality if you did not have some landmark that would guide the users. So of course, color is one thing, and I have seen very creative uses of sound as well in many locations. So yeah, definitely, these are also factors at play.
Yeah. Let's see here. I also have one more here. Which is the most challenging environment to guide a user? Like, do you have, like you mentioned, hospitals, because it's like stressful and you're in like maybe in a position you don't have your vision, clear vision, or you're hurt somewhere and so on. Is there any other environment that you seem like it's really challenging to guide actually the user of the building?
Okay. The perception of the design thinking in architecture is very different internationally. So my personal opinion, and I'm not saying this because I am in Sweden or Scandinavia, but here many things are taken care of. This mindset is very well adopted compared to many other places in the world. But I would say that children are a group that are often forgotten, almost as if so they have to make do with the structures that have been made for grown-ups. I have actually seen schools and kindergartens being designed in extremely challenging ways, or ways that make it challenging for children. But more generally, any environment where you're going to have new people come in and go, and people not coming in regularly, I would say that presents a big challenge. Because no matter how bad a building is, if you are using it every day, you become used to it. And I mean, we tolerate a lot of buildings like that because we have no other choice. I think it was Churchill who said it in some context: we shape our environment and thereafter the environment shapes us, right? It's become some sort of a cliche in this community, but I think it's worth repeating here. So yeah, if you have a place where people will come and not come again, or new people will come all the time, this is where it's extremely hard to anticipate all the requirements. And the post-occupancy analysis that we talked about, it's especially useful in these situations, not only when the building has been immediately built, but once it's become functional after maybe, let's say, a year or so. So you need to keep coming back, and you will start discovering new things to do some cosmetic surgery on. And it's very hard to break down walls. It costs a lot of money, but you still can do things like re-implementing the signage or playing around with colors and things like that. And over time, some of these tricks have become pretty standard. So in hospitals, you will see zones are typically color-coded, and that is done to aid navigation. And airport design also is something where everything I said right now is very challenging and pretty useful.
Yeah, on this point, I was thinking how important it is, for example, when you do these interventions related to color, to get into perspective of like color blind people, especially when they are designing for hospitals, they try to take this into consideration a lot. So you really learn from the process. And I think the most challenging environments are large-scale public buildings, when you really need to consider inclusivity. And many designers nowadays that try to think with this perspective, it's mostly not the idea of like the design needs to like scream inclusivity, but to be open to many different groups to feel comfortable to navigate. So I think it's really challenging with buildings that really need to embrace different communities. And I think the tools are not really helping in this process until now.
Have you actually been like in the process of a new building?
Yes.
Yes, you have.
Yeah.
So both of you?
Mm-hmm.
Yes, yeah. Also together and then also separately in different projects. So the new Parkland Hospital, which we mentioned, it's meant to be a replacement of the old Parkland Hospital in Dallas, and we were a part of it right from the design phases and the post-occupancy evaluation, and there are several other instances of this. But I point that one out because it was one of the largest projects. It was made with a budget of $1 billion and the largest public hospital at that time. So that was pretty interesting to work on.
Thank you. I really appreciate that you will come here. Is there something more that you want to share before we wrap this talk?
Yes, I do want to make a plug here. So I mentioned other domains that we are interested in. Architecture is one application outlet of our work on AI. And the video that you see here, Vasiliki is presently involved in conducting some experiments involving autonomous driving. So if there was a future talk, I could imagine AI for the design of autonomous vehicles. If there are people from the local community listening, you're welcome to reach out to become a participant and see what's happening here in this particular domain.
You got one here.
You're welcome.
Thank you. Thank you. I'm looking forward to it. Yeah. So, and I'm also looking forward to actually see a building here in Örebro, where you have been part of the process. That would be really cool.
Sounds fantastic.
Yeah. Well, thank you so much again. I really appreciate that you took your time and share all your knowledge and your research.
Thank you very much.
This is our last seminar for this spring, and we will be back in the fall again. So thank you so much for listening, and I'll see you in the fall. Thank you.